Last year, I had the pleasure to be here and tell you a little bit about how we do machine learning at AirHelp. And this year, I actually would like to continue that story. So let me start with a short recap on what happened last season. You're flying somewhere. Maybe it's vacation, maybe it's business trip, maybe it's your family that you want to visit for Christmas, whatever, and your flight is delayed. Now, according to European Union regulation EC261, if your flight is delayed over 3 hours, you are entitled to compensation. And airlines sometimes pay. Sometimes they don't. My company is working as a proxy between the passengers and airlines to make sure that if you are eligible for compensation, you will get paid. Now, to represent you, we need permission from you, obviously. This permission comes in the form of a signature on a document called assignment form, and hopefully this signature looks more or less like this. From time to time, our customers are getting a little bit more creative, though. And we actually don't want to send this to the airline as a proof that we can represent you. So in such cases, we actually ask you, as our customers, to try again to send us the signature. We used to, what we have to do to make sure that we are not sending those to the airlines, we actually have to review every single such signature. And we used to have employees looking at every single one of them. As you can imagine, we have roughly 2 to 3 million such signatures a year. Reviewing 3 million signatures a year is quite a lot of work. So what we've done, we've created a model. This is convolutional neural network. And last year, I was telling you a little bit more how we developed it, how we deployed it, and so on and so on. Now, this convolutional neural network went into production. In production, actually executed quite well. As you can see the numbers, the acceptance part is the accepted part is about correct signatures. So if we're getting a correct signature, we're getting quite good results with this model on detecting that we should pass it to the airline. We cannot really rely too much when it comes to rejecting a claim. As I said, this is a model we deployed into production, and this is how the previous season ended. The question comes, should we do better? And this is the key business question. Whenever you're thinking about building a new model or improving the quality of a model you have, the first question you should ask yourself is, does it bring the value to the business? Otherwise, you won't get compensated for it. What's the ROI, and so on and so on. And in our case, the problem with the model we have is that it's quite decent when accepting the and production. I mean, when I'm saying quite decent, I mean production decent. So something that we can rely on production. When it comes to accepting the claims, we cannot really rely on it when it comes to saying, hey, this signature is incorrect. So actually, you should ask our customer to write the signature again. This is why the answer to this, again, 2-3 million signatures and so on. This is why in our case this question is answered in our case as yes, we should do better. Then the next question is, can we do better? And if you think about the examples I've shown you, it's actually not a trivial question, because then you have a customer who's sending us something like this. I mean, obviously, he's making fun of us. So we should send him a request to send us his signature again. And the question is whether we can even build a model that will detect such things. Well, the thing is, we did ask and this was caught by a person on the model this time, we did ask our customer to send us the signature again, and instead of a signature, he sent us a copy of his passport. So this is a real signature, obviously. And this made us thinking that maybe when creating a new model, we should go down to the basics again and review what does it mean to have a correct signature, what does it mean to have an incorrect signature. And so we selected a population of incorrect signatures, and we actually categorized them into 3 groups. Dots and lines, I'll get them in a second. The incorrect signature means pretty much that there's this funny picture and we are basically rejecting it. An agent's mistake. Agent mistake means the signature should be actually accepted and sent to the airline, but one of our employees decided wrongfully that we should ask the customer for additional work. Dots and lines means literally what it says. This is an example of dot and line signature. It's another example of dot and line signature, or some simple curves that we're getting. Now, if you look at those numbers, if you look at those categories, it greatly simplifies the problem, because if 80% of cases are sort of trivial, and then the rest is equally divided between agents' mistakes and cases which actually should be caught but are quite complex. This can be a funny picture, this can be initials, things like that. Then we realized that the only thing we have to solve here is this dots and lines. If we catch those dots and lines cases very, very well, we can actually ignore the rest. Now, the one more question here is whether those numbers are correct. And I'm not a statistician, but a little bit of statistics come in handy here. From time to time, obviously what you're doing here, you're taking a sample. So in this case, you can do a simple trick. You can treat dots and lines as one group, the rest is the other group. This is effective binomial distribution. Applying central limit theorem, you calculate confidence intervals. In our case, for the sample size we've had, the confidence intervals were less than 5%. So even if we're at the edge, it's still quite convincing that the dots and lines are the only problem here. How should we attack it? There are 3 options that we've taken, and we actually did implement POCs for all 3 of them. Standard thing you do in image recognition, so neural networks. The second thing, anomaly anomaly detection, because as you can imagine, the amount of incorrect signatures is actually quite small. It's 1 to 2% out of the whole population. And the third option is analytical approach. I probably won't spoil a surprise if I say that the third one won. And this is the one I will focus on today. with analytical approach I will be showing here today, this is this piece of presentation, a few slides, and the actual implementation is a work of my colleague, so I'm just using it here. How do you do such analytical approach? First, you do the image preprocessing. You're thinning the lines, you're rotating the picture, you're scaling up, scaling down, depending on what you're getting. Then you're detecting complex shapes, detecting dots, detecting intersections. The goal here is to focus just on the pieces of picture that are relatively complex. You calculate direction vectors. The reason why we're doing this is because we want to divide the complex shapes into sections, curves, so more simple elements. And if you have direction vectors, then you can assume that whenever there is an abrupt change of a direction vector on a line, it's probably the beginning of a next curve, next section. Having curves gives you another opportunity. You can talk about monotonicity here. So you can split the picture into decide whether the curve is monotonic or non-monotonic. Again, Cartesian quarters, if the curve goes through more than two Cartesian quadrants, sorry, the curve is non-monotonic. You identify different independence areas on a picture. You calculate separately their complexity. And what you end up with is effectively, in terms of machine learning, a list of features. Fill ratio, number of dots, number of lines, number of monotonic, non-monotonic curves, and so on, and so on, and so on. And this is effectively a feature engineering. Now, having those features, the obvious thing from, again, ML perspective is to build a model. We tried it, we've created a model here, but we've done also one more thing. Because we thought we understood those signatures quite well, we created a linear combination of those features by hand, and weights were just decided by us. It turns out that our hand-chosen weights were actually equally good as our best models, and from maintenance point of view, execution time, and so on, they were actually way easier, way faster, way cheaper. So we ended up with purely manual model in this case, even though we did try the machine learning algorithms here. And how did it go? Well, quite well, actually. This is a comparison of our previous convolutional neural network that was used in production and the model I was showing you here. The previous model was already quite well at accepting correct signatures, but this model is actually way better. And the thing that we wanted to achieve is ability to rely on a model when it comes to rejecting the incorrect signatures. So as you can see, going from red to blue on the second row, it started allowing us. When you have a model, the one thing you do when you do the evaluation is also look at some examples on when the model makes mistakes. In our case, these are the correct signatures, presumably correct signatures according to our employees, that our model rejected. These are the incorrect signatures that our model rejected. Now, I'm not sure what you see. When I'm looking at those pictures, I don't see much difference. Like we're somewhere at the moment, we're somewhere at the edge of deciding whether it's actually even a signature or not. In this case, or in this case. So this is the model we've built. This is obviously something we put into production as well. And we are quite happy with the result. The question is again, should we do better? Again, the business question, again, the ROI analysis and so on. And if you look at the previous examples, you're probably noticing, you're probably having already some ideas on what the model could still be catching, what are the cases that we're missing and so on. But in this case, we're actually already quite happy with the results. So again, coming back to business calculations, doesn't make sense to invest in this anymore. So the answer is no. We shouldn't do better. And that's the end of a technical story part I wanted to share with you. There are pretty much two reasons why I'm telling you this. The first one, well, I think it's cool. This is image recognition, and we all know that for image recognition we use neural networks, nothing else. Except when we don't. And the second reason is, personally, I like battle stories from real production models, real production problems that were solved, deployed, and actually worked. But there's also a higher level question here. The reasons we do not do machine learning, at least back in my company. If I had to come up with one single reason, this should be the inference. With hand-tuned models, with hand-built models, we have way better understanding of what's happening underneath. And it actually very often means that from business perspective, from the perspective of how we can utilize such a model, it brings us more value than having a sort of a black box-ish model that is doing even a little bit better. Maybe it was a little bit cheaper to develop, but it's hard to tell what's inside. So we don't do machine learning image recognition, and this is, by the way, this is false. I mean, we haven't done machine recognition, we haven't done machine learning in this particular project. Still, in most cases for image recognition, neural networks win. But in this particular case, we really, really well knew what we were looking for. So there are more typical cases where we started with some prediction models, and we ended up with analytical approach. And these are key metrics predictions. You can imagine that if we're dealing with compensation from the airlines, what's interesting for us is how many customers will come to us, what would be the behavior of airlines, or how the whole market will behave, how often the airlines will be delayed, and so on. It turned out that if we have simpler models that are more stable, if we're looking just at historical data, we cannot really predict certain disruptions that are happening for the first time. And in our business, it happens often. The volcano is blowing, or there is some huge international strike, or the oil prices go up and down, and they impact our business. These things, or Brexit. That's a great example from our perspective, because this is a different jurisdiction. if we have a manual model, we can quickly adjust. We can quickly understand on whether this model will work or not. And the last thing is process decision. As you can imagine, we have an army of people who are doing customer support, are getting your documents, reviewing your documents, deciding whether your claim, your request to represent you actually is valid or not, whether we even have a chance to win the case. A few weeks ago, we decommissioned a machine learning model we had in production for over 2 years. The model was deciding whether we should go to court with your case or not. As you can imagine, going to court and losing is costly for us, because then we are not actually getting any money, you're not getting any money. And so we don't want to go to court with lost cases. And we had XGBoost powered model that was trying to assess whether we should go to court or not. We changed it with a relatively complex but handmade decision tree. And this is something that is working on right now for 2 reasons. First, with handmade decision tree, we can very, very precisely explain our lawyers why we're making a certain decision. And also adjust it very easily in case the decision turns out to be incorrect. And there's a second sort of funny reason. Well, we were able to reduce power consumption from our servers to like 40% of the original consumption when we moved from statistical model to heuristics. It doesn't mean we're leaving machine learning at all. There are still some cases where we find it really, really useful in practice. The first area are all the off-the-shelf models. If you're looking at Google, if you're looking at Amazon or Microsoft, they have pretty amazing teams and pretty amazing models that you can just use. And I doubt that we can compete with them regarding picture recognition or translations or speech recognitions. These are the things that are useful to utilize. And the second area we focus on is text processing. It's not only NLP. It's also the decision whether an incoming email contains your flight itinerary ticket, or once we have a ticket, extracting all the information about your flight from this e-ticket. So if you think about how many hundreds of different formats such emails and tickets can come up with, then you have multiple languages, obviously. Then using a bunch of ifs won't do the job, and we were trying, so I know what I'm talking about. This is the end of my talk. I wanted to share you a little bit. I wanted to share with you a little bit of our experiences in practice. We've been dealing with this type of stuff for the last 3 years, and yes, well, thank you very much, and enjoy the rest of the conference.